Check it out now, y'all.
NanoHub U, online instruction.
Hi, we're back again, and this time we're going to try and explain to you the optical absorption processes that occur when light interacts or passes through a medium. And in the process, we're going to define some fundamental rate constants. These rate constants are extremely important if you want to understand how a laser operates. And so we'll discuss lasers in the following lecture. But we'll set everything up by defining some important parameters in this lecture. So it's important for you to pay attention to the definition of these three rates that will appear in the middle of this lecture. Those are going to be critical for understanding the next lecture. I guess I'd like to begin by a classical discussion of absorption of light. The problem is an old problem. It was solved back in the 1860s, actually, by August Beer. He gets credit. If you have a material, a chunk of material of length L, right, and you pass light with intensity I naught at some wavelength lambda through this material, and you just simply ask the question, how much light comes out the other end, then you can show by very simple arguments that you can define a transmission of the light through the material is the ratio of the intensity I that emerges divided by the intensity of light that's incident, and that depends exponentially on the length of the material through which the light is traversed. So in this case, we evaluate x equal to L in this exponential formula, and this coefficient alpha then tells us something about how the light changes, how the intensity of light changes as a function of delta x as the light moves through the medium. And I think this law here you'll find in all the textbooks is referred to as Beer's law because it's used all the time to describe absorption of light in different materials. Nowadays, these absorption coefficients are published everywhere. I just give you an example of the absorption coefficient versus wavelength for a number of interesting semiconducting materials. And what you learn from this diagram is that the absorption coefficient changes by quite a bit. It changes by about 1 million over a very small range of wavelengths. And there's structure and sharp drop-offs in the absorption coefficient, and these sharp drop-offs are, of course, related ultimately to the electron energy states that exist inside these different materials. But this would be a typical result of this very standard absorption measurement that's sketched out schematically here. Of course, we try to understand things at a little bit deeper level than just the results that are plotted in that previous slide. And so I just asked the question, what's absorbing the light, right? When the light goes through the material, what's absorbing the light? And the answer, of course, is it's the atoms inside the material that can take the light. The light can be viewed as a distribution of photons passing through the material. If the material is comprised of, let's say, quantized energy states like I've got drawn here, then whenever the incident photon energy is equal to the energy difference between these two states, then you can absorb that photon and it'll disappear from the exiting beam, and so the intensity will drop down. And that's fundamentally the explanation for this absorption coefficient alpha. What we'd like to do is we'd like to try and analyze that situation in a little bit more detail. And to do that, what we have to do is we have to focus on the number of electrons that are in each energy level. So in addition to the energy levels, which has been our focus, our sole focus up to this point in the course, right? We're now going to start asking questions about how many electrons N1 are in energy level E1 and how many electrons N2 are in energy level E2. And in addition to that, since it's possible that these energy states could be degenerate, we're going to designate the degeneracy of these different energy levels by this number G1 and G2. So this is just telling you how many different ways, how many different sets of quantum numbers you need in order to have an energy level E1, how many different quantum numbers you need to have an energy level E2. And we're imagining that the material through which the light is passing is now a collection of gas atoms. And in particular, we're going to focus on hydrogen atoms because that's what we know something about. It turns out that process is, an analysis of that process is very, very interesting. And it was performed with considerable insight by Einstein in and around 1917. And what he did is he was able to define 3 fundamental atomic processes that are useful to understand this absorption of light. And so I'd like to go through these 3 processes, and then in the course of this lecture, I'd like to define these processes in a little bit more detail and work out some simple arithmetic to give you some feeling for how these this qualitative discussion in this slide, how that translates into actual quantitative numbers that are extremely interesting. So the first fundamental optical process that Einstein identified was something called spontaneous emission. And he said that if an electron is in an energy level E2 and it drops down to an empty state in energy level E1, then a photon is emitted. And he defined the spontaneous emission rate. In other words, how many of these transitions per second occur in a collection of gas atoms. So this discussion is all focused on rates, and whenever you hear a rate, that just typically means how many per second of these events occur. And so, for instance, the spontaneous emission rate would tell you how many of these transitions could occur per second, right? The second fundamental process that he identified was the absorption rate, right? And the absorption rate is simply that if you've got a photon coming into a collection of gas atoms, if that photon interacts with an electron in energy level E1, the photon can disappear, the electron can absorb that energy, and the electron then undergoes this transition to a higher energy state. And so he identified something called the absorption rate, which is the probability per unit time to go from 1 to 2, right? So that was the second process that he identified. The third process he had to cook up, right? He was in the process of trying to understand more about Blackbody radiation, and he recognized in the analysis of Planck's Blackbody law, he recognized that there was a process that was omitted that went beyond these 2 simple processes, and he referred to that as a stimulated emission process. And the way the stimulated emission process goes, it says that if you have an electron in energy level E2 and another photon comes by, and if that photon interacts with that electron, it can stimulate or induce this electron to go from this energy level down to this energy level, so that you got 2 electrons or 2 photons coming out. And furthermore, the 2 photons that come out are locked in phase, right? There's a synchronization of the electric and magnetic fields of the 2 photons. So this is like a light amplification, right? You put 1 photon in, you get 2 out, and it relies on this incident photon interacting with an electron in the upper energy level state. So that's called stimulated emission rate, and it's a process that Einstein had to invent in 1917, and it turns out this process is exactly what you need in order to produce a laser. Of course, it wasn't realized in 1917, but that's another story that we'll talk about in the next lecture. So with a simple understanding of these three processes, it's a fair question about what you want to calculate now. What do you want to understand? And the focus quickly goes to relative populations. In other words, you have a collection of gas atoms, some number of gas atoms, and two are in the upper energy level state, another collection of the atoms totaling N1 are in the lower energy state. You've got a radiation field that interacts with those gas atoms, right? That incident radiation field is going to be specified by some function U of F. So this is going to tell you the energy density in this incident electromagnetic field. And what you like to know is you like to know how much comes out, right? What are the characteristics of the light that come out? So you're going to be calculating transitions to go from 1 to 2. You're going to be calculating transitions to go from 2 to 1, and you're going to be using these fundamental definitions of optical processes in that calculation. So that's sort of the plan for the remainder of the lecture. So what I like to do is I'd like to define these transition probabilities in a mathematical way, and I do that in the next 3 slides. The next 3 slides are the key points in this lecture, and the key points that I'm going to focus on are circled by red boxes. So there's going to be one red box in each slide, and that red box is going to define the seminal equation that we're going to use towards the end of the lecture. So to make the discussion a little bit more simple, we're going to also assume that these degeneracy factors G1 and G2 that we introduced, we're going to assume that they're equal to one another. That just allows us to remove the degeneracy differences between energies E1 and E2. It just simplifies the arithmetic a little bit. So we can do that without loss of generality. If you want to put in those factors later on, it's reasonably straightforward to do so. So let's begin, right? We're going to define the spontaneous emission rate. That is how many transitions go from energy level E2 to E1 in a second of time. And we're going to define that by some coefficient capital A sub 2, 1. So this is the rate by spontaneous emission, and an electron can go from energy level E2 to E1. And what we're interested in is if initially there are N2 electrons in energy level E2, how does N2 change with time? Well, N2 is going to change with time. It's going to, in the way that I've indicated by the equation in this red box, right? If you know this emission rate, and you know the number of electrons initially in that energy level E2, then the change in the number of electrons in energy level E2 is just going to be given by the simple product of A21, that's the rate, times the number N2. To turn the rate into a number, you've got to multiply by a time interval dt. And so this is the definition for how dN2 changes as a function of time. The minus sign just indicates that dN2 is a number that decreases with time, right? So you need the negative sign here in order to recover the fact that N2 is a decreasing number with time due to this particular atomic process. So that's the definition of the spontaneous emission of photons due to this transition from energy level E2 to E1. That's pretty simple. The second process ties into the discussion of the absorption at the beginning of this lecture, right? What Einstein did is he defined a coefficient called B sub 1, 2. And this coefficient B sub 1, 2 times the incident radiation field U sub F. So this is the energy density contained in this incident radiation field, right? The product of those two numbers then tells you what the rate of absorption of photons is by this two-level atomic system. So again, the question that you tend to focus on is you tend to focus on if there's N1 electrons in energy level E1 to begin with, how does N1 change with time? And the argument is very simple to what we've already been through, right? The change in N1 with time, it's going to be linear in time, so the change dN1 is going to be proportional to the time interval d2, and it's going to depend on the number of electrons, the number of atoms that have electrons in energy E1, so that's this N1 factor, and then it's going to depend on this rate, B12 times U sub F, where U sub F is telling us something about the incident radiation field. Again, the negative sign is just telling us that N1 decreases in time, right? Because electrons are going up, that means N1 has to go down, and that's expressed by this negative sign. Okay, so that's the second important result that Einstein was able to derive just by thinking about this problem in 1917. The third rate is the stimulated, it's also referred to as the induced emission of electrons from energy E2 down to energy level E1. And that stimulation or inducement of photon emission is seeded. It's triggered by this incident photon, right? And again, this incident photon is specified by this radiation field that specifies the energy density of the photons coming into this collection of atoms. Now, U of F is kind of a murky quantity in this discussion. We'll derive an explicit expression for it in a few minutes, but it's left vague and it's a general way of expressing the incident radiation field. And what Einstein said is you need this process in order to understand Planck's final formula for the blackbody radiation problem, right? And so he defined the rate to go from 2 to 1 by stimulated emission as a coefficient B sub 2, 1, so 2 to 1 times the incident radiation field U of F, right? That's the rate. And in a similar way, the important equation that results from this definition of the rate is that the change in the number of electrons or the change in the number of atoms which have energy E2, right, is equal to, is proportional to the time delta T, is proportional to the number of atoms that already are in energy level E2, so that's this quantity N2, and then it depends on this rate factor B21 times U sub F, which is defined here. Right, so this is the third important equation that's required to understand these atomic absorption and emission processes. So, you know, at the outset, it looks like we're just defining coefficients that don't have much in the way of physical meaning, right? But Einstein's genius was able to take these fundamental definitions and turn them into something that we can actually measure, and that actually turns out to be extremely important for the discussion of atomic processes in atoms. And I'd like to try and illustrate that very briefly in the remaining part of the lecture by just asking the question, if I have a two-state system with N1 atoms in energy level E1, N2 atoms with energy level E2, right? I like to ask in equilibrium, what happens to N1 and N2? Well, in equilibrium, you would expect that the number of atoms that make the transition from 1 to 2 is just equal to the number of atoms that go from 2 to 1, right? That's an equilibrium process. And that equilibrium process perfectly describes the blackbody radiation process that occurs when you take an object and you heat it up. You take an oven, you heat it up to a high temperature. the light that's coming out of that oven is ultimately related to atoms inside the oven that undergo transitions. And if everything is in equilibrium, then the rate that goes for the atoms to go up in energy has got to equal the rate for atoms to go down in energy. Well, you can take the three equations that were underlined or were boxed in red on the previous three slides, right? And you can then say that given this, this requirement, you can say that the change in the number of atoms in the upper state with respect to time due to absorption has got to equal the change in the number of atoms in the upper state due to the spontaneous emission, plus this stimulated emission term that Einstein postulated, said you need, right? So this equation has to be true for this equilibrium condition to be met. And if you go back and you look at those three equations in those three red boxes, you can see that you can write each of these three terms, okay, in terms of the number of atoms in the upper level and these different rates that depend on the incident radiation field U sub F. So this equation here is directly follows from this equation. This equation directly follows from this equilibrium constraint that we've imposed. The great thing about this is now you've got an equation and you can actually solve for this elusive U of F, right? This thing that we've just written down symbolically. You can solve for this in terms of Einstein's rate coefficients and also the ratio of the number density, the number of electrons in state N1 divided by the number of electrons in state N2. That comes out. So you can, you know, there's about 2 lines of algebra to go from here to here. You can check my arithmetic. But this is the equation that you need for U sub F. It turns out that you can estimate this ratio of N1 over N2, right? And that can be done using classical thermodynamics. We will derive that expression in a later lecture in about 2 weeks from now. Right now, I just make the statement that Boltzmann solved this problem. And the Boltzmann solution is simply, you know, if you have a collection of atoms and you put them in a quantum system that has discrete energy levels and everything's in some equilibrium at some temperature T, the question then becomes, how do these atoms distribute themselves in these discrete energy levels? And what Boltzmann was able to show is he was able to show that the number of atoms in energy level E sub n is equal to the number of atoms in the 0 ground state energy level times this exponential e to the minus E sub n over K Boltzmann T, where K Boltzmann is this constant that comes out of the ideal gas equation, actually. So the answer to the question, how do these atoms distribute themselves in these energy levels when everything's at an equilibrium temperature T? The answer is they distribute themselves exponentially with temperature, according to this equation. And it just simply means there's always more electrons or more atoms in the ground state, fewer atoms as the energy goes up. And the way the number of atoms decreases with energy is exponentially with the energy E sub n over K Boltzmann T. So for a two-state system, right, that's what we're worried about now, we can ask the question, well, how many atoms are there in N1? How many atoms there are in N2? We can use this result, since we're only interested in the ratio of N1 over N2, right? Remember, right? We're just interested in this ratio N1 over N2. We're not interested in equations here. Proportionalities are good enough because the proportionality constants will cancel when we take the ratio. And what we find is that this ratio of N1 over N2 is this just e to the exponential E2 minus E1 over K Boltzmann times T. And this energy difference, E2 minus E1, the energy difference between these two energy levels, is just HF. That's the energy of a photon that would be emitted if an electron undergoes this transition. So the upshot of that discussion and again, I'll just say we'll derive this equation in more detail later on in the course, right? The upshot of that discussion is that we can now rewrite this expression for the energy density of the electromagnetic radiation in terms of Einstein's fundamental coefficients, but now we've got an expression for the ratio of N1 over N2, and that expression is this exponential that depends on frequency of light that's emitted when the electrons undergo these transitions, and it also depends on the absolute temperature T that the atoms have when they're distributed in this system. So the temperature T has to be expressed in Kelvin for you to do this calculation. So now something very interesting happens, because if you recall from the first week of the course in 1900, Planck says, oh, I can explain the blackbody radiation if I assume that the energy density U of F is given by this complicated equation. And you say, well, where did that complicated equation come from? And Planck had some argument that is best left in history, right? But experimentally, this formula matched the experimental data very well. So this is the correct answer. And now, based on Einstein's coefficients, right, we've got an equivalent expression from the previous slide for this same quantity U of F. So we can now compare these two expressions, and we can then get some insight into what these rate constants that Einstein defined in a very abstract sense, what these rate constants actually equal. And so just by direct comparison, you can see that the ratio of B1 over B2, B12 over B21, that ratio has to equal unity, right? And so that implies that these two rate constants are equal. And from the prefactor for U of F, you can see that the spontaneous emission divided by the stimulated emission rate has to be equal to this quantity that multiplies this exponential term, right? So we now have expressions for these various constants, these rate constants. They're interrelated one with respect to another. And what I always like to point out is that if we can find one, if we can just find one of these quantities, right, then we can calculate the other two, because they're all interlinked by these two equations. So, very interesting result, okay, extremely interesting result. I'd like to just end the lecture by working through an example to show you how these rate constants can be measured and how they can then, how a measurement can then be used to calculate, for instance, the other rate constants. I just asked the question, you know, if you somehow put a lot of electrons in energy level E2, and then you measure the decay of these electrons with respect to time back to this energy level E1, I just worked through the arithmetic here to show that in the absence of any external radiation, so that means if I let U sub F go to 0, right, and just watch how these electrons cascade back to the lower energy state, what I can do experimentally is I can measure an exponential decrease in the number of electrons in this upper energy level N2, and that rate at which the electrons decrease is just precisely related to this coefficient A sub 2,1 that Einstein defined. So if you can measure the rate at which the electrons decrease from the upper energy level, you have a direct measurement of this coefficient A sub 2,1. And then I work through a case where I measure A21. I just say, okay, I measure it to be something like 2 times 10 to the 8th per second, which basically means there are 2 times 10 to the 8th transitions per second for electrons to go from, let's say, the 3p to the 2s level in hydrogen. So that's something I can measure experimentally. And then once I know that number, then I can use it to calculate the rate of this stimulated emission, B sub 2,1. And I just work through the arithmetic. And once I know the coefficient B sub 2,1, then I can calculate the rate of stimulated emission. So in other words, I can estimate how many photons are being emitted in this collection of gas atoms by other photons that are passing through it. And of course, that calculation depends on a model for U sub f, right? And here I just assume that the gas atoms are in thermal equilibrium at some temperature T, so that allows me to use the Planck Blackbody expression for U sub f, and that allows me then to calculate the rate at which the rate at which atoms go from the upper energy level to the bottom energy level in a collection of hydrogen atoms. In this case, I picked a temperature of 750 Kelvin just to pick a number. And what I find that the rate of stimulated emission at this low temperature of 750 Kelvin is very small. There's only 3 × 10⁻⁵ transitions per second due to stimulated emission, while there's 2 × 10⁸ transitions per second due to the spontaneous emission. So for this case, right, spontaneous emission wins big time. There's very little stimulated emission that occurs. And it's just an example of how you can use these rate constants to estimate what the fundamental atomic process is that gives rise to the light that comes out of a collection of gas atoms. So this discussion then sets up a more interesting discussion about lasers and allowed transitions in collections of atoms. And that's going to be the topic for the next lecture. So come on back and we'll give you a quick overview of how these concepts can be then related and used to invent something called a laser.